Hi there, this lesson is Kepler's third law, part of A-level physics, gravitation. So the first thing is, where does the law actually come from? So when you have, say, a planet, let's call this E for Earth, and something is in orbit, some satellite maybe, and it orbits the Earth, what describes it, this motion, the velocity v, is the gravitational force making the satellite accelerate towards the Earth, but then the velocity keeping the satellite from falling into the Earth. So the gravitational force, the G m1 m2 over r squared, which is Newton's law of gravitation, you will make that equal to the centripetal force, because the gravitational force is making this satellite exhibit circular motion. So that's the principal expression. So we can calculate these r's, cancel these m's, and we're left with v squared equals gm over r. So if you watched my previous videos on orbits, you will have seen this before. So what we can do now is substitute in the equation v equals 2 pi r over t, which is an equation from the further mechanics module. So if we square the 2 pi r over t to get 4 pi squared r squared over t squared, we can make that equal to gm over r. So I'm just going to do that now. So 4 pi squared r squared over t squared equals gm over r. And what we can do is, now we've got a relationship between r cubed and t squared, if we take this r up to this side. So r cubed essentially is equal to gmt squared divided by 4 pi squared. The gm divided by 4 pi squared is just a constant. The mass of the body that's being orbited is constant, g is constant, and 4 pi squared's a number which is also constant. So we can see there's a relationship, r cubed is proportional to t squared, and that is Kepler's law. You might be asked in an examination to show where that comes from. That's the process. If you need to watch it again, just rewind. And what I'm going to do is show you how we apply this relationship of r cubed proportional to t squared to solve questions. So let's have a look at one. So in this question, the average radius of the Earth's orbit is given as 15 times 10 to the 10 meters. The average radius of Mars' orbit, 23 times 10 to the 10 meters. And the question is asking, calculate the amount of time it takes Mars to orbit the Sun. So what we can do is use Kepler's law. So remember, it's r cubed is proportional to t squared. And we can do that for both the Earth and Mars. They're both equal to some constant. So I'll show you the full process. So r cubed is equal to some constant times t squared. But that holds for both the Earth and Mars. So essentially I could write Earth, so radius of Earth's orbit cubed, time period for Earth squared. And then I can also write the exact same thing, but this time for Mars. They're both equal to the same constant. If you remember the constant from the previous slide, it was gm divided by 4 pi squared. So what we can do is make these equal, rearrange both of these formulas to get k and make them equal to each other. Now from that, you might be able to answer this question. If you want to have a go, just pause the video. If you want me to finish the example, just carry on watching. So it would be orbit for Earth cubed divided by time period for Earth squared equals the same for Mars. Then it's just a matter of putting the numbers in. So the radius for Earth cubed is, well, it's 15 times 10 to the 10, but both of these quantities are to the same power, so we can just do 15 cubed divided by time period for Earth. Well, that's just 1 year, so we'll leave this in years. 1 squared is 1. Equals distance from Mars. Well, that's 23 times 10 to the 10, but we've neglected the times 10 to the 10 on the left-hand side, so we'll do the same here. So that's just 23 cubed, divided by the time period for Mars squared. So you should be able to see that the time period for Mars is equal to, we've got 23 cubed divided by 15 cubed square root. So that gives a time period for Mars of 1.9 years. So on the next page I've got an example that's basically the same but different numbers. So if you want to have a go at that one. And then I'll take you through the answer. So same again, Kepler's law, r cubed equals k t squared. So we'll do Earth first, so orbit of Earth cubed divided by time period for Earth squared. And then the same for Mercury, divided by time period for Mercury squared. Then it's just a matter of putting the numbers in again. So the distance for Earth is 15 times 10 to the 10, but they're both times 10 to the 10, so we can just ignore the powers. So distance for Earth cubed would be 15 cubed, divided by the time period. The time period for Earth again is 1, equals the distance for Mercury. So that would be 5.79 cubed, divided by the time period. So time period for Mercury squared. So once again, the time period for Mercury is equal to the square root of 5.79 cubed divided by 15 cubed. And that gives us 0.24 years. If you want to check any of these answers on Google, they are correct. Kepler's law is still accurate today. So let's move on, let's do another one. So for this last question, if you want to have a go, please do, just pause. Pluto orbits the Sun every 248 Earth years. The average radius of Earth's orbit is 15 times 10 to the 10 meters. So what you're going to do is calculate the ratio distance from Sun to Pluto divided by distance from from the Sun to Earth. Okay, and then I'll take you through this. So once again, it's r cubed over t squared. Equals r cubed over t squared. And on one side you need Earth, and on the other side is Pluto. So the distance to Earth cubed is 15 times 10 to the 10 cubed. Divided by time period for Earth squared, which is 1. Equals distance of Pluto cubed, which is what we're after, divided by the time period 248 years squared. So the distance of Pluto cubed is equal to 248 squared multiplied by 15 times 10 to the 10 cubed. Put that in your calculator and then take the cube root, and that will give you a distance to Pluto of 5.92 times 10 to the 12 meters. Then we just need to finish this off doing the ratio, distance from Sun to Pluto divided by distance from Sun to Earth. So it will be 5.92 times 10 to the 12 divided by 15 times 10 to the power of 10. And if you calculate that, you'll get 39.5. So essentially, Pluto is 39.5 times further away from the Sun than the Earth is. So hopefully that's helped. And I'll speak to you soon. Thank you.